Hello, this is Xiao, a PhD student from Columbia University. Today I'm presenting a joint work with Microsoft Research titled Teaching Language Model to Self-Improve through Interactive Demonstrations. Up until today, there are many methods to improve a language model's output beyond using a simple QA format. For example, consider solving a math question. Calculate 4 times 1 minus 2 times 3. One common practice to obtain high-quality answer include prompting a few examples as in few shot prompting, or using a chain of thought template to elicit a better reasoning trace. In this simple question, both methods can achieve the correct answer given a sufficiently powerful language model. More recently, another prompting method is proposed for ideally more complex questions. It is called self-improvement prompting. Similar to chain of thought prompting, this method first let a language model provide a chain of thought-like answer attempt. But different from previous approaches, it then continues by prompting the language model again, asking for feedback on its thought attempt, and then giving the feedback, refine its previous update if needed. More generally, this feedback update loop can be run multiple times for problems the language model may struggle to find the right answer in one shot. Although prior work has found the self-improvement approach plus LLM can further improve the performance, we find there are many issues when applying this technique to smaller, more cost-effective language models. On two method reasoning tasks, we find that applying the self-improvement technique actually decreases performance compared to using other simpler methods. We find that this happens because for small language models, the ability to reflect on its own solution is weak and highly error-prone. In fact, the self-improvement process often creates more compounding errors and throwing the overall performance. Next, we find that other proposed approach, such as training the language model with the LLM demonstration of self-improvement, also didn't work well. Why? We find that this happens because the method reasoning ability of the LLM and the smaller ones are very, very different. For example, they often make different type of mistakes as well as a different number of mistakes. As a result, these LLM demonstrations are irrelevant given the current model's capability, and hence fine-tuning of these data became ineffective. So self-improvement is useful, but many of the current approaches fail when it comes to small language models. What do we do? Similar to some prior work, our idea is to specifically train the small language model with its ability to generate critical feedback and update its attempt. But different from prior work, we aim to train the small language model in an online fashion. Instead of learning from expert demonstrations, our idea is to use the use LLM or Python scripts to provide edits to the small language model's attempt, and then we use the edit history to train the small language model. On a high level, this means that first, we let students make all the attempts. Then, we ask the teacher to check for mistakes and propose edits based on the student attempt. Finally, we combine the interaction data into the dataset and train a small language model. We designed this approach with the hope that this edited feedback and update will be more incremental and manageable for small language models to learn. We call this approach tri-post. More specifically, it is implemented as follows. First, we want to allow the student to make the best attempt possible. So, given an input from training data, we prompt a small language model, for example, llama 7 billion, to attempt to generate the attempt, feedback, and so on. Then, we aim to obtain checks and edits from an expert on the task, starting from reviewing the feedback generated by the small language model. For math-heavy tasks, this can be often achieved by simply using Python logic to parse and evaluate expressions. For language-heavy tasks, we prompt the LLM to edit part of the original feedback. Then, we also want to review and edit updated attempt generated by the small language model. This is achieved mostly using LLMs, since intermediate steps may include reasoning in the natural language. First, we construct a prompt consisting of the original attempt, the edited feedback, and all the intermediate steps in the original attempt up until the error mentioned in the feedback. We then prompt the expert LLM to complete the rest of the steps, conditioned on all previous information as an edit on the update. In general, the above loop can be repeated for many times, and we can perform that on every training question in the dataset. This results in a trajectory for each question, where data involves the teacher incrementally changing the student's attempt. We then filter out the trajectories that fail to reach the correct answer and reformat them into a uniform format of self-improvement triplets or directly correct pairs. Before directly piping into training, we also rebalance the dataset as it's naturally biased towards self-improvement triplets. This results in a training dataset collected in an online fashion. Given this data, we simply consider weighted supervised fine-tuning with emphasis on learning the feedback improvement steps, as that's the goal of the work. Finally, we note that this loop of online data collection, post-processing, and training can be run multiple times. How do we evaluate our approach? We consider 4 tasks from Big Bench hard, where small language models struggle at those tasks, and the tasks themselves are easy to be split into easier harder subtasks. For example, a 7 to 13 billion model really struggles on multi-step arithmetic, and we can use the depth and number of brackets in the question to split them into easier subtasks or a harder for training or a harder subtask to measure the generalization ability. Throughout all tasks, we want to see how often can the model self-improve correctly and whether it is helpful to improve the overall performance. We first answer the second question, where we find that after 3 iterations of try-post, it can outperform all prior approaches, with improvements both on the easier subtask and on the harder ones. To answer the first question, we then analyze how much of the correct attempts did the model perform self-improvement. We find that compared to prior methods where small language model plus self-improvement often result in wrong answers, here about 10 to 20% of the correct answers were generated from self-improvement attempts. Given that now models can self-improve normally, we then wanted to investigate which part of the algorithm was most critical for this ability to emerge. In the separation study, we find that simply distilling the small language model with LM demonstration shown in pink is worse than simply supervised fine-tuning on the correct answer. And only when the online data is added to training, which is shown in the purple bar, can it start to exceed a simple supervised fine-tuning. Next, we also investigated how modifying the rebalancing step in try-post would affect the overall performance and self-improvement frequency. Compared to our heuristic of setting 40% of the data as self-improvement and the rest as directly correct pairs, we can use the model's performance to automatically adjust this ratio, which we call try-post auto. Here, the idea of the red highlighted box is that if the model only has 20% accuracy, then 20% of the training data will be directly correct pairs, and 80% will be self-improvement triplets. We find that in this setting, the model performance further improved, yet self-improvement frequency became near 0. We believe that this indicates first, learning from mistakes is still very useful, but second, if the model can directly solve a question, it prefers to do that instead of attempting self-improvement. Besides, we also find 2 interesting artifacts from our experiments. First, during training, we tracked the number of self-improvement trajectories that made it into the training buffer. We find that as training goes on, there is less and less data we can collect. This not only results from our model being slightly better in each iteration, but also we find that LM really starts to struggle to provide the correct feedback, even though it can itself solve the task for near 80% of the time. We find that we believe this casts some doubt on LM's capability. Being able to generate the correct solution does not imply and understand the solution in depth. Next, we find the frequency of small language model attempt to self-improve is roughly proportional to the training data distribution. This is surprising as we thought that this frequency should be determined by the difficulty of the question. But in hindsight, it may be intuitive, as the less self-improvement data is in the training, the less likely it has learned to self-improve at test time. Finally, limitations. First, we found that using stronger language models as edit models could strongly affect final performance. One aspect is that cheaper LLMs such as ChatGPT often are unreliable at detecting errors, hindering the quantity and quality of the collected data. But of course, using more powerful language models will incur more cost. Second, although allowing models to self-improve at test time can give better performance, it can take considerably more time to generate compared to more direct approaches such as channel-stop prompting. In summary, we first identify a problem with small language model performing self-improvement, where prior work showed that LLMs can use this to further improve performance, but prompting or simple decision approach with smaller language model does not work. We then propose Tripost as an online approach to teach the small language model to self-improve. The idea is to use LLM or Python script as edit models to modify the original attempt and train the small language model. We find that Tripost can then be used to further improve the small language model's performance in various settings. And finally, in our analysis, we find the process of self-critiquing and self-improving is still hard and error-prone even for large language models. In general, we believe our work suggests that training methods can extend beyond the traditional input-output pairs, with online edit history also proving to be a valuable source of learning data. We also believe our work opens new possibilities to leverage LLMs to enhance the more cost-effective smaller ones. Thank you for listening.